G'day. Today I'm talking a little bit about metrology, which is the general name given to the measurement of things, and running through a few of the common terms that are used so that if someone comes along and talks to you about precision or accuracy, you understand the professional terms that are being used rather than layman's terms. There is a slight difference, and so I'll be talking about accuracy and precision and uncertainty and a few other things like that. And hopefully it'll be interesting and informative. Now I have been having trouble with the audio with this camera. I'm not quite sure why. It's probably me, but just in case the audio is not as good as it could be, apologies for that. So these are the three terms we're talking about: repeatability, accuracy and precision. Repeatability is how often you can get to the same number, basically. And so that's very important, if particularly from a statistical point of view. If you want to be sure that your measurement is correct, you do it a number of times. And so having equipment which is repeatable is a good idea. Okay. Accuracy is how good is the equipment, how close is it to the target value or the true value. So if you've got something which is, for all intensive purposes, absolutely 25 millimeters long, and your measuring equipment says it's 24.5, it's maybe not very accurate. Okay, depending on what you're measuring it with, that may be the best you get. Okay, and the third one is precision, and precision relates a little bit to the accuracy in that when we talk about precision in measurement, we're talking about how close is the value you're getting in terms of the number of significant digits to the true value. So if I have a ruler which is graduated in meters, and I'm trying to measure something which is 25 millimeters across, right, that's not very precise. I'm not going to get there. If I use some form of trick spectrometer or spectral analysis or something like that, that also can give me measurement, then I'm going to be a lot more precise. Whether it matters, of course, is another matter. But they're the three things that when you start talking to people who measure and potentially make things, precision things for a living, they're the terms you're going to run into. So if you see here, my efforts at nail croquet have yielded a reasonably tight group of holes here, and this is pretty much the textbook definition of repeatability, that you're getting values very close to the mean value. Not necessarily that you're right in the middle of the target, but you've got a group. The reason for that, of course, is that means that by a simple adjustment, or hopefully by a simple adjustment, you can then move that group over to your target through calibration or whatever. So you can see here that I'm a lot more accurate. I'm not lots close to the target with my Ninja gear cutters. I can get much better accuracy right where I want to be. So far I've talked about repeatability and I've talked about accuracy, but there's a third term that's often used, and that's precision. So that's basically the difference. 0, 10. So the problem here becomes, if you're using this target, you've got 10, you've got 0, and you've got a whole bunch of things in between. If you're using this target, you've got 10 or you've got 0. And so when we talk about precision in measuring things, we talk about how well the measuring device is able to discriminate between one value and the next. So typically, if you've got a steel rule which is graduated in, say, centimetres, the rule of thumb is you can judge that to plus or minus half a division, so half a centimetre. If you've got a steel rule which is divided into millimetres, you can then theoretically get down to measuring to half a millimetre. So basically, that's repeatability, accuracy, and precision. One term that gets used occasionally is uncertainty, and that can be a little bit confusing as well. I guess the equivalent of uncertainty is a tolerance on a dimension when you're making something. The uncertainty is really the tolerance on the device making the measurement, which says, is it good or is it bad? As it says on here, that's standard at 20 degrees C. Uncertainty is really to take out the variations you get from temperature, from material condition, from measuring force, and so on. So if this rule was at, say, 30 degrees, because it's been sitting in a hot shed, and I brought something in from the house which was sitting at, say, 20 degrees, there would be a slight variation because of the expansion and contraction. The good thing, I guess, for a home workshop is it doesn't matter too much, because the sorts of uncertainties we're talking about are down in the micron scale. But when you're looking at the precision of devices, the more precise they become, the more uncertainty gets in there. Something like this, it's graduated to microns, so you could say, well, it's good to that, but because of thermal effects, that could be plus or minus 5 microns or something like that. Vernier scales, once again, thermal effects may come into things. A digital caliper like this, typically these things are regarded as plus or minus 0.05 of a millimetre. Other things that might influence uncertainty would be the squish of the material you're measuring. If you're measuring something soft, and depending on how much force you put on it, that might change your measurement, so that's part of uncertainty. Temperature is a big one, so if there is a temperature difference between what it is you're using to measure and what it is you're measuring, then there's uncertainty involved there. If the temperature differs from the standard temperature, even if both parts are the same temperature, there's a bit of uncertainty there. You might say also, if you're using an electronic device, it could be there's some uncertainty in the processing there, that this might process to 3 significant digits, or it might process to 5. You don't know. You could probably find out from the manufacturer, but that would add to the uncertainty. However, as I said before, for the home workshop, typically the tolerances and things we're working to, uncertainty doesn't matter too much, but it's worth knowing what the term means, because someone may throw that up if you're talking about precision things like gauge blocks and calibration and all that sort of stuff. Another thing that we occasionally talk about when talking about measuring things is a thing called ABBE's principle. ABBE, with an accent mark over the E, I think it is. And what that basically says, if you're measuring something, you need to be, your most accurate, best measurement is in line. And an illustration of that is this thing. This is an inside micrometer, and when you're using it, it's measuring between those 2 points. Your measuring device is directly through those 2 points. On the other hand, if you're using something like a digital caliper, as you can well imagine, if you're measuring something in there and you exert a bit of extra force, you can bend the caliper, and you may not see it, but you will get a slightly altered reading. And the same holds for a typical micrometer as well. They can also be subject to this. So it's just something to bear in mind, that when we're measuring, we want to get a consistency of force on the application. We want just enough to measure, but not too much, which is why people say, okay, when you use a micrometer, you go 2 clicks and that's it. Click, click, not click, all in one, and not click it until you really feel like stopping. When talking measurement, there are a couple of errors that we talk about. One of them is parallax error. Now, this is an old style analog multimeter, but you can see there's a strip of mirror behind it. And the reason for that is that the scale and the needle are in a slightly different planes. They're not separated by much, maybe a millimeter or so, but they're separated. And so if you were reading from the side and trying to work out where the needle lined up, you might get it wrong. Okay, I don't know whether you can see that. And so the strip of mirror there is simply so you can line up the needle with itself and say, right, the needle is lined up with itself. I'm now 90 degrees to the mirror, or the mirrored surface, the scale, and so therefore what I see with the needle is correct. Okay, so that's parallax error. This is possibly the mechanical equivalent of that problem. This is an interrapid bore gauge, and if I'm very careful, you've got a needle there. Okay, and so once again, if you're not perfectly square to that needle, you could get an error of measurement. That's also the reason that micrometers, verniers and so on, at least the better made ones, have got the scale coming down on a cone like that. They're trying to get these divisions as close as possible to these divisions so that you don't, or you minimise the possibility of getting that parallax error in there. The last type of error that I was going to mention was cosine error. This is a really hard one to illustrate. There are probably stunning examples which I'll think of after I've finished doing this clip, but it's basically, if I have my calipers in there like so, and I measure that, and I'm directly on the diameter, I get a correct reading. If I'm off slightly, if I don't have those quite right, okay, I can get a slightly erroneous reading. Okay, and it's really about the angle of the measuring equipment to the angle of the dimension you're trying to measure. Hopefully that'll give people some insights on how these terms are used in metrology. And thanks for watching, and thanks for those who've inspired me.